Hello everyone, I'm Deepanshu Malik. I'm the co-founder and CTO of EndoVision. We are a Hong Kong-based medtech company, primarily building SAMDs, AI SAMDs for endoscopy. Today, I'll be walking you through how to build real-time AI applications on and also deploy them on the edge devices. These are medical-grade carrier devices that can be easily integrated into the clinical workflow. So let me first tell you a little bit about our product. So our product's name is Cerebro. It's a quality control tool for endoscopy. What it does is it tracks anatomical landmarks inside the stomach and ensures that uh, clinicians have at least seen them once during the inspection, hence ensuring the full coverage of the stomach. So this is how the endoscopy screen looks. The real-time view is the live image from the endoscope. On the right-hand side, you see three or four different widgets. These are all AI outputs that we put on the screen. On the extreme right, you see progress. These are the 34 landmarks that we have broken down stomach into. And as soon as doctor looks at each landmark, it is marked as checked. We are also tracking how much time they are spending on each landmark inside stomach. And there are some actionable quality alerts which tell them if they need to rinse or inflate the stomach. So this is a small demo of the application. So as soon as doctor reaches a particular landmark, the progress automatically updates. And at the end of the procedure, once the doctor has inspected the full stomach and taken the endoscope out, our software automatically generates the most representative image of the stomach of each landmark and puts that as a photo documentation. So this is about the application that we are going to see today, how to build such an application. One of the major challenges in building such an application where we are tracking stomach landmarks is that stomach has very similar looking areas and which makes it very hard for image-based detectors and classifiers to correctly predict which landmark we are at. So this is why it requires a bit of temporal context. So let me, yeah. So this is what our AI pipeline looks like. We have raw live image from the endoscope. This is fed into the first layer, which is the deep learning models and the computer vision algorithms. This is where all the spatial features are extracted from the images. These spatial features are then fed into our post-processing module. This is a temporal feature aggregation module, which tries to improve on the degraded frames or similar looking frame problems and makes a decision based on temporal context. And it creates these sparse events where landmarks are detected as events as well as any quality alerts that are shown are detected as events. These events are then passed to the output layer, where the output builder creates the final overlay that is superimposed on top of the raw image to show the final output. So if we look at all the three layers in the inference layer, we have deep learning models and vision models. So we have five classification models, one object detection model, two computer vision algorithms. Now this layer requires a total of roughly 4 GB of GPU memory. Uh, the temporal feature aggregation module it's a lightweight module. It runs on CPU and it requires 256 MB of system memory for keeping the temporal and historical data. And it runs on both x86 and ART64 architectures. The output builder is the third layer. This requires 2 minutes of historic frames. This is because our software is built in a way where our algorithm uh, sometimes qualifies frames from the history when the confidence levels are high, and so it requires to cache those frames. So this module requires 2 GBs of system memory. So overall, the most fundamental runtime requirement of our pipeline is that it should be able to complete all of its job and maintain real time frame rate. So that gives us 50 milliseconds per frame, which translates to 20 frames per second. So this is the benchmark that we need to reach to for our algorithm to work properly. So just a overview of Holoscan SDK. So some of the most important concepts that are required for building an AI pipeline. So essentially, a Holoscan application is built of directed acyclic graphs. A fragment is a single directed acyclic graph which consists of nodes. These nodes are Holoscan operators. Operators are the ones that are actually performing the operation on data, and they communicate with each other via named ports. Um, a single fragment executes in a single process. That means that all the resources are shared within that graph if it belongs to the same fragment. Operators are like a microservice. They have input ports and output ports. On the input ports, they receive the data. As soon as they receive the data, they can make the computation. You can compute on top of it, and then using the emit API, Python API provided as part of Holoscan SDK, you can emit on the final output on the output port that can be transmitted to the next node of the graph. So yeah, each operator can define multiple input and output ports. The third most important concept is the condition and scheduling term. So these operators, they have this life cycle of start, compute, and stop. So start is where you initialize the context and any other initialization that you want to make during the real-time life cycle of the operator for each frame. This is continuously called compute method. So this is waiting for new data to arrive at the input port. Once the new data arrives, then the compute executes, and then it goes back to the idle state where it is polling for the new data. The stop method is where basically everything you implement that you want to unlink or you want to free up the memory. So any operations before termination that can be implemented. So this is very important to know that the default scheduler is the greedy scheduler, where it will continuously poll the compute method for new data. There is also a threaded scheduler for complex pipeline where you want to offload some of the work to the background. Um, this is also possible using the scheduling term. And finally, the overall application, a Holoscan application is a collection of one or more fragments. A multi-fragment distributed application can be created using Holoscan, and there is inter-fragment operator communication is also possible. Although it makes a copy of the data and there is some synchronization overhead, but it is worth it if your application has some parallelism in it. Um, so overall multi-fragment applications, like there are many advantages. Isolated resource allocation, so that means that if your pipeline has different CPU workloads and different GPU workloads, different parts of your pipeline, then you can club them into different fragments so that resource allocation can be done properly and can be utilized in an optimal manner. And also you can this also enables parallel execution of tasks, and you can also have fine-grained control over the resources of GPU. So for example, the pre-processing of may require lesser GPU than the inference fragment. So this kind of tuning can be performed, configuration and tuning can be performed in a multi-fragment application. So to build the application Cerebro, so I have uh, a simpler version of the application I'm going to go through. So first step as part of development of the application is to write down your workflow. So to design your workflow, so over here we have input frame that is coming directly from the endoscope. Then we have the pre-processing layer. This is where a dynamic crop or resizing, batching, and aggregation, any other augmentations can be performed. Inferencing layer is where we have our deep models, our deep learning models, and the computer vision algorithms. And the post-processing module is where we have the additional algorithms, temporal feature aggregation module, and also the final overlay output that we are going to generate. So once you have designed your workflow, the next step is to convert them to operators. So over here, I'm using, this is a GI Genius Edge Device Genius Source Operator, which it has, it connects to the capture source and gets the live image from the endoscope to the Holoscan pipeline. All the other operators are defined by EndoVision, and except for the inference operator. So this is a multi-model AI inference operator, which is an inbuilt operator provided by Holoscan. And finally, the output operator is again provided by GI Genius, that directly overlays the image on the output screen. Once you have defined all the operators, the next step is to group them into fragments. So whichever fragment processes whichever workload, so it's going to be totally based on the workload of uh, each different process. So it could depend, it will totally depend on the type of application that you are building. So in our case, the input part was totally done with a different API and had different resource requirements. So that is why we have clubbed it into a different fragment. Similarly, pre-processing, inference, both of them have been put into the same fragment. Post-processing has been broken down into two fragments, one for the temporal thresholding and the temporal feature aggregation module. The second one is the output builder. And finally, the Genius overlay operator is put into the output fragment. Uh, so over here, as we see, like input and output are provided by the edge device that we are going to use later to deploy on. But for development, it is recommended. So since you are going to do it on your own system, so it is recommended to use some other operators that can help you. So we built this FFmpeg operator that helps us stream from any other V4L2 source or from a video file. And also for the output, we are using the inbuilt HoloViz operator that comes along with the Holoscan SDK. So once we have designed all the operators, now we are going to define all the interactions between these operators. So the flow of the directed acyclic graph. So over here, video genius source operator provides the raw frame to the pre-processing operator. The processed image is then transmitted to the inference layer as well as the output builder for caching the image. Uh, these outputs are then uh, flowing directly to the output builder, and then the transparent overlay is transmitted to the Genius video source output operator. Sorry, Genius video overlay operator. And overall, this graph needs to run within 50 milliseconds to meet the requirement of 20 frames per second. So application defining, so for simplicity, I'm not defining any fragments in this sample application. So I'll just show one fragment. So this is how you use the add flow API to define which operators have which ports linked to each other. So signal and input ports, for example, over here are linked to Genius video source and image pre-processing operator. So this graph is depicted over here at the bottom. This is how the operators are defined within the Holoscan application. So you can define your custom uh, operators and have them named operators with different memory allocations. So these are the main methods that, as we discussed earlier as well, that we need to override uh, as part of the implementation. So setup is where we define all the input and output specifications. So these name ports then are used to communicate and receive and transmit the data to the next nodes. Start is where we initialize any initialization, any state variables that we want to keep, we can keep over here in the start method. So over here is an example of the implementation of a compute method for a pre-processing node. So it is important to keep in mind until the receive API is invoked, there won't be any transfer of data from one node to the other. Once the data is received, then the rest of the code is executed. And finally, at the bottom, we can see that it is transmitting all different kinds of data to its different output ports. So stop method is where you want to, so this is a small implementation where we have a stream running. And before we end the Holoscan application, we want to free up all that memory and any other resources that the streaming operator is using. So this is a good example of implementation of stop method. Uh, yeah, and within the Holoscan context, they have provided the SDK comes with the multi AI inference operator, which can be configured directly via key value pairs. So over here we are giving model path map. So providing all the ONX paths that need to be loaded during the runtime. Similarly, there is pre-processing map, which maps which models input is provided in which variable. And finally, the inference map to map the inference to the output variables. Um, Along with this, like once the Holoscan application is run, only the first time it is going to load the ONX and create the TensorRT engine files. From the next time, it is going to cache. It is going to use the cached version of the engine files. So you can actually safely delete the ONX files once from the Docker image itself. Once you have the engine files, this is useful if you are giving your models as part of an edge application where you have little control over security or protection of your models. So this is the application, the sample application that we have just created. So we are going to run this within the Holoscan Docker environment. So over here you can see on the left hand side. So these are the objects that we have overlaid on top of the feed that is coming on the right hand side. So as soon as the doctor enters the patient, it will, so on the top we see the timer has started and different landmarks are now getting qualified. This is basically the same demo that I showed you, but now this is built with the Holoscan, and you can see the user interface is a bit different as well. Moving on. And yeah, I think so. The development environment, it's very flexible and agnostic tool. the environment or the laptops or the desktops that you have, you can use the Docker-based development environment. NGC Holoscan Docker images available at NGC, and you just need GPU and Nvidia drivers. That's it. So it's very easy to get started up on developing Holoscan applications. For this is this we found very useful. So since our requirement was to finish the pipeline within 50 milliseconds, so we added another edge in this graph, which transmits the timestamp at which it received the image and the time it took for the output builder to finish its work and create the transparent overlay. So overall, this helps us not just monitor that our pipeline is healthy, but it also gives mitigates the risk for the clinicians. So if they see that the AI is lagging or something is wrong with the system, they can quickly shut it off. In terms of packaging, so Holoscan comes with the Holoscan CLI, which is very handy for packaging the applications. So you just copy your models, install your code as a package, and these images can be then directly run on the intended hardware that you want to run on. So this particular example shows a DGPU, basically RTX 3000 series is what we ran it on. Similarly, there are for IGX ORing, you have the iGPU Holoscan image that can be used. There is another example of where. Sorry, I think. Yeah, so this example, we are going to show you another application. So this is atrophic gastritis. So apart from tracking the anatomical landmarks, so this is another application that also tells in real time if there is atrophy inside the stomach, and it also characterizes the extent to which it has spread inside stomach. So this is basically where we are using segmentation models as well as combining the information with the landmark tracking tool. At the bottom, you see this. This is a flat diagram of stomach, flattened diagram, where we are showing right now we have observed that there is atrophy till C1. As the video progresses, we'll see that all the atrophy has been registered in this Kimura Tokomoto diagram. So I just want to pause here and just want to tell you that so you typically most of the applications may just require you to put a box in real time or maybe a segmentation mask. But our requirement was putting these diagrams and some complex objects on the screen. We realized that it is also time consuming. So not just pre-processing, inferencing, post-processing, but also the overlay creation needs to be given its due share of optimizations. So the way we do it, we have a separate operator for overlay. So during initialization of this operator, there is a generator that generates all the states of all the objects that we saw on the screen. So these are cached in an asset cache. During the real-time execution, when the compute is executed of the overlay operator, it combines the asset cache information along with the dynamic content that it wants to show and creates an array-based canvas that can be overlaid on top of the live feed. So the example that we saw previously in the video, so these are the states that we create for each and every object, and then we cache them so that we can just quickly replace them during runtime without having any overhead of display creating the overlay output. So essentially, so this is a 1920 by 1080 canvas, which matches the raw image size. Uh, and once all the assets and the dynamic content is combined, so overall, this is what the final output looks like. So there is significant difference if we create the output overlay on CPU versus if we are creating it on GPU. If you are using NumPy, for example, just to paste a 600 by 600 image that we see over here, this one. So it takes 9 to 10 milliseconds. We do it on CPU. But if you are using QPy, it is almost nothing, like very little time. Permuting image channels. This is a common thing that is performed during resizing and during pasting the images onto the canvas. So all these add up to 13 to 14 milliseconds for NumPy and 2 to 3 milliseconds for QPy. So this is a huge gain that we saw in our pipeline. Um, and this allows us to remain real time and be able to show our content. So it is very critical because so over here, like the all the left hand side content can still be near real time, but anything you are showing on the live image has to be uh, exactly real time, less than 50 milliseconds. In fact, quite a lot less than 50 milliseconds, so that the display time can be enhanced as well. So we do, as I was mentioning, GI Genius. So we have developed our own device, as well as GI Genius is from Medtronic and Cosmo Pharmaceuticals. They have a platform which they are opening up for companies like us, so that we can publish our applications on their platform. So ours is VM500. This is Quadro RTX 3000 series GPU. It has a single output channel capture device. So both live image and the overlay are shown on the secondary screen because of the limited capabilities of the capture device. It has an initial latency of 220 milliseconds, which is okay for secondary screen, but it is not possible to put this on the main screen because of this limitation. On the other hand, the GI Genius device, this has two output channel capture device and a similar GPU. But most importantly, it has a hardware-based keyer implemented in the capture device. So this is very useful because if the app crashes or AI workflow crashes, you would want your clinical workflow to continue. So this works even if the device is off, it will still relay the output to the main screen. Uh, in this case, like we don't have to uh, add the live image plus overlay. We can just supply the transparent overlay over the content of the live image. It has latency of less than 1 millisecond, and it is tailor-made for main screen. So I would like to tell you a little bit more about GI Genius because this is the main device now we are using for distributing our application. So it is built for third-party AI applications. It has, as I said, RTX Quadro GPU, and the capture device is very advanced. It supports GPU direct RDMA technology that allows uh, the Holoscan operators to be directly able to uh, get the data from the capture device into the GPU memory. This is critical because for any low latency application, it is not possible without such direct memory access. On top of it, they have built the Genius OS, which is basically they have abstracted out all the firmware drivers related to GPU, related to the capture device, related to all the IO operators. So this gives us as an SAMDI application company a lot of freedom, where we don't have to worry about, because GPU landscape changes very quickly. The firmware, the new drivers, the new SDKs, they the speed at which the changes are happening is very fast, and the regulatory approvals and everything, like it takes a lot of time. So even right now we are using Holoscan 0.6 uh, and in production, although we have moved to higher versions in our development environment. But just to let you know, like for SAMDs, the version upgrades and maintaining the compatibility metrics can become a bit of a headache. On top of it is the third layer, which is the application layer, where we can simply provide our Docker application, which can directly be run on top of this device. Overall, like the Genius source and the Genius overlay operators, they don't add any overhead on on your pipeline. So overall, it takes less than 1 millisecond uh, if we pass it through a test operator. In terms of application performance, as we seen previously for overlay, we saw NumPy and QPy comparison. There is a similar comparison for any other data transfer that is happening between operators. It is recommended that we use QTensor or QPy. As long as the data remains in GPU, there will be less copies created and there will be faster communication. So over here we can see significant difference as we reach the higher numbers in terms of image size. We see vast amount of difference in terms of time consumed for transferring the data between operators. So just to summarize the GI Genius and the Genius OS platform integration, so it provides a great abstraction. It has a powerful I/O interface and real-time zero latency transmission to the screen. It features powerful GPUs. Right now, it has RTX Quadro, but we have tested on IGX Orin developer kit as well, which is coming up next. So as I said, like the pace of development of the industry is very fast, and medical devices need to go at their own pace. So it decouples the hardware from application, takes care of the hardware and firmware upgrades, ready to use capture APIs, works on both discrete and embedded GPUs, um, provides IO abstraction. We don't have to worry about streaming and rendering the output. It is done in conjunction with the capture device that is used, along with the two channels for the output for merging the overlay and the live image. In terms of integration, I think we have already talked about this, but the Docker-based deployment and distribution, they do provide technical support as well for integration and web sandbox for testing. Overall, it took us 20 days for ramping up on Holoscan and 30 days to implement our. Uh, so bear in mind, like we had a previously working pipeline, which was built with Ray and different other frameworks. So the workflow was already there. So we were porting our existing workflow. So it took us 30 days to implement this part, 30 days to improve and test and package and get it ready for deployment. So overall, 3 months to integrate and test on GI Genius device. Some of the advantages of using Holoscan, as I said, like previously, we had a very different architecture where we were using mix of CPU and GPU. But since we have moved to Holoscan, things have been brilliant in terms of latency, in terms of memory management, better resource utilization, and faster inferences. So main advantages are low latency interaction between different operators, zero copy operations directly on GPU. This we have already seen, like NumPy and C to QPy already takes a lot of time. It Holoscan provides built-in operators for multi-model inferences. This is off the shelf, so you don't have to spawn your own server, or you don't have to worry about serving. So it's very straightforward and very configurable. So very low code. Vast variety of pre-built operators are available in HoloHub repository. Just like we saw Genius video source and overlay operators, there are Deltacast and other capture devices who are providing all these operators in the HoloHub repository. Uh, Hassle-free development and deployment with Docker and Holoscan CLI is also very helpful. And again, GPU Direct RDMA, that's the key for ultra low latency streaming applications. Um, so this is required for any clinical workflow, endoscopy related workflow that wants to show real time results. There are some inbuilt operators: video stream replayer, video stream recorder, and holoviz op. All these operators are inbuilt and can be used during development. But we found that some of the operators can be quickly created just for the development environment where you don't have to rely on the hardware.